the car headlights will be lit by an electrical current passing through the tether. If the lights stay on during the test, it'll show the tethers could transmit wind-generated electricity from the aerial turbines. The winner will be the tether that can carry the most weight with the headlights still running. By nightfall, the team is ready to test the tether made of steel. A voltmeter will record any decrease in voltage as the electricity flows through the tether. A stress gauge will measure the weight as the cars, linked together by chains, are lifted, one by one.
I've got 12 volts going in. We're checked and ready here. You're good to go, so you can go ahead and start the lift.
To pass the test, the tether has to suspend all 5 cars with their headlights on.
All right, I'm starting to get 200 pounds.
Stable on the electricity.
All right, the second one's off because we're at 4,200 pounds. We're at 6,370, 6,370 pounds. So we are just over 3 tons. The sheathing's broken.
The orange skin of the tether is coming apart, a sign the steel cable is stretching.
It's getting longer, it's gonna go. There it goes.
I guess that's what you call a compact car.
The steel tether broke at 3 tons, 2 tons under the target goal. That means if the steel tether had been holding an airship, it would have broken under the strain of a mere 32 km/h wind. There's only one alternative, and Jennifer hopes this one is up to the job.
Aumenta em um coeficiente intelectual alto ou muito alto, é heterossexual, o seu aspecto físico é normal e até atraente, tem amigos e amantes, tem até esposa e filhos, é o que muitas pessoas chamariam um tipo fixe. Este homem é um assassino em série.
Assassinos em Série. Estreia domingo, 23 de agosto, às 22h10, só no Discovery.
Team member Jennifer Langwell is testing competing tethers for Fred Ferguson's revolutionary lighter-than-air wind turbine. The steel cable snapped well before its target weight. Everything's now riding on the copper-wrapped Vectron tether. Jennifer is still worried this high-tech, untested plastic cable will break under the strain of a 5-ton load.
So this is your design, Jeremy.
This is it, the real deal.
Are you ready to start this?
Let's do it.
Ready to see it.
Okay, let's start the lift. What we're looking for is 9,400 pounds. We're at 2,200 right now. We need to see 5 cars off the ground. 4,100. 4,100 pounds on the tether. Getting ready to go for 4 cars. We're at 6,400 pounds now.
The steel tether snapped at this weight.
We're at 8,400. So we are 1,000 away. 1,000 away from what you need to make your experiment work.
We're almost there.
We're at
5 cars.
Let's watch it there and make sure it holds.
The Vectron tether is holding all 5 cars with lights on. That's when Jen ups the ante.
Let's lift that last car. So the tether has 12,000 pounds. 12.4, 12.5, 12.6, 12.8.
It's off the ground. It's off the ground.
12.8, and it's off the ground.
There you go. 6 cars.
Check the volts.
The headlights are still on.
The volts are holding. All the headlights are lit.
Good stuff.
All right, Jeremy.
There.
Awesome job.
That's great.
Well done.
Thank you very much.
Absolutely well
That's a
done.
lot of work. That's great.
The Vectron tether has surpassed all expectations. 2¼ centimeters in diameter, can hold an astounding 6 tons of dead weight.
I'm extremely impressed with the Vectran. I never thought the thin strands of hair would actually hold up 6 cars. I think this is going to work.
It's now time for the ultimate experiment. A few days, Fred's crew will have fully assembled a prototype aerial turbine. What they'll need next is the right location to fly it in the wind.
This is Virginia. I think I found what I'm looking for here.
Kevin O'Leary, the team's logistics expert, has found the perfect spot in the Allegheny Mountains, part of the Appalachian mountain chain. Conventional wind turbines can't work here because ground winds are almost non-existent. But if the aerial turbine can generate power at 90 meters, it'll prove it can work anywhere in the world. It's a wild, empty meadow in the middle of a bowl-shaped depression.
Fred, let me show you this place.
Oh, wow.
Isn't this beautiful?
Yeah, really beautiful.
This is Allegheny Mountains, completely surrounded. It's totally isolated.
No kidding. With the circular range of mountains, any kind of standing wind turbine would be pretty near useless.
Precisely why I chose it for this test. Because your whole concept was it can work anywhere.
It's now up to Fred's ground crew to make success happen. At the test site, the team starts to examine the best place to deploy the turbine.
I have some photos of the location right here. Okay, well, we've got to move the equipment into place, and we've got to select the best spot. And that best spot, from my evaluation, is this particular area right here.
Fred needs the ground conditions to be as calm as possible during the initial deployment. The tree line should give him this protection.
What do we have to do next?
Well, what we have to do is, first off, I need to bring in the guy that knows what he's doing, which is Dale, and he's our field marshal, and he's going to watch over the equipment and plan on the actual operation itself.
Hey guys, what's happening? Hey.
What is the point at which we have no choice but to go?
When we start putting gas in it. Once the helium is flowing into the balloon, and you start to get, helium will rise very quickly into it, and if any winds would come up or a storm would pass through, it would really collect it like a large sail and could blow it right off.
The turbine's component parts are put together. The first piece to be assembled, the 25-meter horizontal truss, is the turbine's main structural support. Then 185 square meters of balloon are carefully unwrapped. Crucial components have been built into the design. The chevron blades that spin the turbine and the central rudder fin are attached to the airship's supportive netting. This spreads rotational forces across the entire balloon.
The netting is an essential structural component of this device. It takes the forces from the blades and transfers them down to the end plates.
The end plates hold the generators. They're installed next. These plates are 120 centimeter diameter aluminium discs that keep the turbine rotating on its central axis. This allows the generators to convert wind power to electricity, sending it down the high-strength Vectran tether to the ground. This is the first time Fred and his team have inflated the turbine. Filled with almost 1,000 cubic meters of helium, it could suddenly drag them across the field.
If the wind catches it, it'll shift across here. It'll move with about the same force as a bulldozer.
Inflating it will take at least 4 hours, but halfway through, the team run into an unexpected design flaw. The weight of the 7-kilo generators has caused the prototype to sag at both ends. It's a problem that compromises the design.
We have this massive weight on each end of the balloon. The only thing keeping it in place is that fine net that you see coming across the top. Now, it's not going to handle this weight on the sides from the generators. My concern is that as this inflates, it's going to droop.
Fred's aerial turbine must rotate on its central axis to produce electricity. But because of the droop at the ends, the alignment between the generators and the main body of the turbine is thrown off. Instead of creating electricity,